After watching this episode, you'll never see the world in quite the same way. And I'll tell you why. In a subtle way, the world is basically a bunch of triangles. Now, maybe this is an experience you've had many times through this course, where it feels like a revelation when it finally clicks. Like, after learning about permutations, you might realize why it's so difficult to find a perfect arrangement of just a dozen or so objects. Or, once you understand normal distributions, you see them pop up in all kinds of places, and appreciate how statistical variation affects so much of what we encounter every day. But triangles take this even further. They're the building blocks of most of the other shapes we've discussed in our geometry unit, and we can use them to describe spatial relationships all around us, from the way we lay out cities to redesigning attics. I'm Jason Guglielmo, and this is Study Hall Real World College Math. So far, we've looked at perimeters, areas, and volumes, which are all ways of measuring how different shapes occupy space. But all of this has missed one crucial element: angles. Whether you're constructing a rooftop, planning a garden, or putting up a wind turbine, all of these rely on the angles between two or more things. Angles are basically the amount one line is rotated compared to another line it intersects with. The smaller the angle, the more the lines point in similar directions, and the larger the angle, the more the lines point in different directions from the point where they cross over. We can make this a bit more precise too. We call that place where any two lines meet a vertex, which is essentially a fancy word for corner. Even if two lines don't fully cross over and just meet at a point, like the corner of a square, that's still a vertex. And a great way to get a handle on angles is by looking at triangles. That's because they're the simplest polygon, which is just a closed shape made of straight lines. Take any two lines at different angles, connect them with another line, and boom, triangle. What's more, triangles help us study the geometry of other shapes since all polygons can be chopped up into smaller triangles. Now, one crucial fact linking triangles to angles is that their shape is pretty much entirely determined by the angles inside of each corner, which we call interior angles. For example, take a triangle with any three interior angles. We'll call these angles A, B, and C. No need for actual values since no matter what they are, the logic still applies. Now let's take another bigger triangle with angles D, E, and F. Apart from their size and the way they're positioned, these triangles look really similar. In fact, they're basically the same triangle. The only difference between the two is that one is a kind of zoomed-in, rotated version of the other. That's because their angles are exactly the same, which gives them the same basic shape. And when two triangles share all the same interior angles, we call them similar triangles, since they're, well, similar. Similar triangles have other important properties too. Let's focus on their side lengths for a minute and label each side length, this time with lowercase letters. Using these new labels, we can show how the relationship between the different sides are the same in each triangle. We won't go into too many details, but basically because all the angles are the same or congruent in our two triangles, that totally determines what side lengths are possible, given the length of any one of the sides. So, because our triangles are similar, the ratio between A and B is exactly the same as the ratio between D and E. And we can say the same for any two corresponding sides. These formulas tell us something important, which is that if triangles are similar and we know the side lengths or the ratio that describes their relationship for one of the triangles, we automatically know it for the other. This comes in handy in lots of different problems. For instance, we can use a smaller triangle that's easier to work with to talk about a larger triangle. To see why similar triangles and their cool relationships might be helpful, let's turn to Rosa, who's converting her attic into an office. Rosa puts up drywall on the walls and ceiling to make the attic feel more like a room, then sets out to paint it. When she stands with her arms fully extended, she can reach the top of one wall, but the opposite one is a bit higher. Connecting the two is the straight, slanted ceiling following the shape of her roof. She starts painting the ceiling using a paint roller that's half a meter long and doesn't get far before realizing it's too short. By laying the roller on the ground and using it as a measuring tool, she finds she's only 2 meters from the shorter wall where she started and has another 3 meters left to finish painting the ceiling. So, Rosa figures she needs to know how far a new paint roller would have to reach to paint the top of the ceiling, so she can buy the right one to finish the job. As you may have spotted, there's a triangle or two lurking around here. First, let's see what it looks like when Rosa gets to the highest point with her current roller. Now, to use similar triangles to solve this problem, we can ignore everything below the height of the shorter wall, since Rosa's outstretched arms hold the roller from that point up. We only need to worry about the height of the roller itself. And we know her current roller reaches half a meter up when she's 2 meters away from the smaller wall. That gives us our first triangle. The bottom length is 2 meters, while the height of the triangle is half a meter. And if we consider how high Rosa's roller has to be to reach the highest point in her ceiling, we see another triangle too. The ceiling still has the same angle relative to the walls, and Rosa's roller is at a right angle to the ground when she holds it straight up, so that angle will be the same too. That means all the angles in our first triangle are the same as this new, larger one, which means we have similar triangles. That means we can use what we know about the side lengths of our smaller triangle to describe the larger triangle and find the height of the new roller she needs. First up, we know the ratio between how far Rosa was able to paint, 2 meters, and the height of her current roller, which is half a meter. That's the ratio between two sides of our smaller triangle. Then we know that the full length of the room is 5 meters. And based on what we just explored with similar triangles, with only those measurements, we can find how long of a roller Rosa needs to reach the top of the ceiling. For now, let's just call it x. As we learned earlier, we know the relationship, or the proportions, between sides in our two similar triangles are exactly the same. In this case, the ratio between the length of the short roller and how far across the attic Rosa got is the same as the ratio between the length of the roller we need to reach the highest point and the total length of the room. This basically gives us an equation that we can solve with a little algebra. Currently, x is divided by 5 in the equation. So if we multiply both sides by 5, we get x is equal to 1¼ meters. So to reach the top of the ceiling, Rosa needs a roller that's at least that long. With that knowledge, Rosa can order a new roller she knows will definitely be up to the task and finally finish decorating her new office. So far, we've talked about interior angles and the relationships between sides for a particular triangle. But with similar triangles, because they have the same relationship between their sides, we can also talk about the proportions between both triangles. Because the sides correspond, we know that the ratio between A and B is the same as the ratio between D and E. Now let's take that relationship and multiply through by B over D. That might seem like an arbitrary thing to do, but when we do that, the B's and D's cancel on both sides. And now we have the ratio that tells us the relationship between pairs of corresponding sides. Let me explain a little bit more. Notice that the sides that look the same on each triangle wind up on the same side of the equation. A and D are paired up in a fraction, and so are B and E, which are both opposite the same angles in their respective triangles. This means whatever factor we need to grow or shrink one triangle to transform it into the other applies to all the sides of the triangle. Like, however much smaller A is compared to D is the same as B is compared to E, and we can apply the same logic to all the different pairs of sides. So we end up with a number that we can use to turn one similar triangle into the other. In fact, we could have flipped the proportions around or used different corresponding sides, and it would all still be true. To sum up, similar triangles can help us work out ratios between corresponding sides of two different triangles, as well as within the same triangle. And that's equally useful in certain situations. We can see this by heading back to Rosa. Say when her original roller got as far as it could, she'd gotten through 3 buckets of paint. Before she buys a new roller, she could also get an estimate of the total amount of paint needed to finish the entire ceiling. Assuming the ceiling is a rectangle, and based on our knowledge about surface areas, the amount of paint would be proportional to the length of the ceiling from one wall to the other. So all Rosa needs to know is what proportion of the ceiling she has left. The amount of ceiling she has left compared to the total area of the ceiling will be the same proportion as the amount of paint she needs to finish in relation to the total amount of paint. And since the triangles are similar, the ratio between how much ceiling she's covered so far and the total length of the ceiling is the same as the ratio between how far across the room she got up to and the total length of the room. That tells us that the factor that transforms the small triangle into the big triangle is 5/2, which is 2.5. 2.5 times the 3 buckets she's already used means that the whole ceiling will need 7.5 buckets. Given she already used 3 buckets, it means she'll need 4.5 more buckets to finish the job. So, with our knowledge of similar triangles, we can solve all kinds of situations involving pretty much any relationship between the side length of each triangle. And with a little ingenuity, we can find or create similar triangles all around us. However, there is something special about Rosa's situation. The particular triangle in her case has one important feature that makes it even easier to work with. It contains a right angle. We call these right triangles, and we can make our lives a whole lot easier using certain mathematical tools especially suited for them, which is precisely what we'll dive into next time. Thanks for watching Study Hall Real World College Math, which is produced by Arizona State University and the Crash Course team at Complexly. If you like this video, give us a like and subscribe. You can learn more about ASU and the videos produced by Crash Course in the links in the description. See you next time.